are going to build. The next layer we are going to build is the feed forward. You can see here. And the feed forward is basically a fully connected layer that the model uses both in the encoder and in the decoder. Let's first have a look at the paper to see what are the details of this feed forward layer. In the paper, the feed forward layer is basically two matrices, one W1, one W2, that are multiplied by this X, one after another, with a ReLU in between and with a bias. We can do this in PyTorch using a linear layer in which we define the first one to be the matrix with the W1 and the B1, and the second one to be the W2 and the B2, and in between we apply a ReLU. In the paper we can also see the dimensions of these matrices. So the first one is basically D model to DFF, and the second one is from DFF to D model. So DFF is 2048 and D model is 512. Let's go build it. Class feed forward block. We also build, in this case, the constructor. And in the constructor, we need to define these two values that we saw on the paper. So D model, DFF, and also in this case, dropout. We define the first matrix, so W1 and B1, to be the linear one, and it's from D model to DFF, and then we apply the dropout. Actually, we define the dropout, and then we define the second matrix, W2 and B2. So let me write the comments here. It's W1 and B1. Of DFF to D model, and this is W2 and B2. Why we have B2? Because actually, as you can see here, bias is by default it's true, so it's already defining a bias matrix for us. Okay, let's define the forward method. In this case, what we are going to do is we have an input sentence which is batch. It's a tensor with dimension batch, sequence, length, and a D model. First, we will convert it using linear 1 into another tensor of batch to sequence length to DFF, because if we apply this linear, it will convert the D model into DFF, and then we apply the linear 2, which will convert it back to D model. We apply the dropout in between. And this is our feed forward block. Let's go have a look at the next block. Our next block is the most important and most interesting one, and it's the multi-head attention. We saw briefly, in detail in the last video how the multi-head attention works. So I will open now the slide again to show to rehearse how it actually works, and then we will do it practically by coding. As you remember, in the encoder we have the multi-head attention that takes the input of the encoder and uses it 3 times. One time it's called query, one time it's called key, and one time it's called values. You can also think it like a duplication of the input 3 times, or you can just say that it's the same input applied 3 times. And the multi-head attention basically works like this. We have our input sequence, which is sequence length by D model. We transform into 3 matrices Q, K, and V, which are exactly the same as the input in this case, because we are talking about the encoder. We will see that in the decoder it's slightly different. And then we multiply this by matrices called W, Q, W, K, and WV. And this results in a new matrix of dimension sequence by D model. We then split these matrices into H matrices, molar matrices. Why H? Because it's the number of head we want for this multi-head attention. And we split these matrices along the embedding dimension, not along the sequence dimension, which means that each head will have access to the full sentence, but a different part of the embedding of each word. We apply the attention to each of these smaller matrices using this formula, which will give us smaller matrices as a result. Then we combine them back, so we concat them back, just like the paper says, so concatenation of head 1 up to head h, and finally we multiply it by WO to get the multi-head attention output, which again is a matrix that has the same dimension as the input matrix. As you can see, it's the output of the multi-head attention is also sequenced by D model. In this slide, actually, I didn't show the batch dimension because we are talking about one sentence. But when we code the transformer, we don't work only with one sentence, but with multiple sentences. So we need to think that we have another dimension here, which is the batch. Okay, let's go to code this multi-head attention. I will do it a little more slower so we can see in detail everything how it's done. But I really wanted to you to have an overview again of how it works and why we are doing what we are doing. So let's go code it. Class. Also in this case we define the constructor, and what we need to give to this multi-head attention as parameter. For sure the D model of the model, which is in our case 512. The number of heads, which we call h, just like in the paper. So h indicates the number of heads we want, and then the dropout value. We save these values. As you can see, we need to divide this embedding vector into h heads, which means that this D model should be divisible by h. Otherwise, we cannot divide equally the same vector representing the embedding into equal matrices for each head. So we make sure that D model is divisible by h, basically. And this will make the check. If we watch again my slide, we can see that the value D model divided by h is called dk. As we can see here, if we divide the D model by h heads, we get a new value which is called dk. And to be aligned with what the paper, with the nomenclature used in the paper, we will also call it dk. So dk is D model divided by h. Okay, let's also define the matrices by which we will multiply the query, the key, and the values, and also the output matrix WO. So this again is a linear, so from D model to D model. Why from D model to D model? Because as you can see from my slides, this is D model by D model, so that the output will be sequenced by D model. So this is WQ. This is WK. And this is WV. Finally, we also have the output matrix, which is called WO here. This WO is h by dv by D model. So h by dv is what? dv is actually equal to dk, because it's the D model divided by h. But why it's called dv here and dk here? Because this head is actually the result. This head comes from this multiplication, and the last multiplication is by v. And in the paper they call this value dv, but on a practical level it's equal to dk. So our WO is also a matrix that is D model by D model, because h by dv is equal to D model. And this is WO. Finally, we create the dropout. let's implement the forward method, and let's see how the multi-head attention works in detail during the coding process. We define the query, the key, and the values, and there is this mask. So what is this mask? The mask is basically if we want some words to not interact with other words, we mask them. And we saw in my previous video, but now let's go back to those slides to see what is the mask doing. As you remember, when we calculate the attention using this formula, so softmax of q multiplied by kt divided by square root of dk and then by v, we get this head matrix. But before we multiply by v, so only this multiplication here with q by k, we get this matrix, which is each word with each other word. It's a sequence by sequence matrix. And if we don't want some words to interact with other words, we basically replace their value, so their attention score, with something that is very small before we apply the softmax. And when we apply the softmax, these values will become 0, because as you remember, the softmax on the numerator has e to the power of x. So if x goes to minus infinity, so very small number, e to the power of minus infinity will become very small, so very close to 0. So basically we hide the attention for those two words. So this is the job of the mask. Just following my slide, we do the multiplication one by one. So as we remember, we calculate first the query are multiplied by the wq. So self.wq multiplied with the query gives us a new matrix, which is called the q prime. In my slides, I just call it query here. We do the same with the keys and the same with the values. Let me also write the dimensions. So we are going from batch sequence length to d model. With this multiplication, we are going to another matrix, which is batch sequence length and d model. And you can see that from the slides. So when we do sequence by d model multiplied by d model by d model, we get a new matrix which has the same dimension as the initial matrix. So sequence by d model. And it's the same for all three of them. Now what we want to do is we want to divide this query key and value into smaller matrices, so that we can give each small matrix to a different head. So let's do it. We will divide into using the view method of PyTorch, which means that we keep the batch dimension, because we don't want to split the sentence, we want to split the embedding into h parts. We also want to keep the second dimension, which is the sequence, because we don't want to split it. And the third dimension, so the d model, we want to split it into two smaller dimensions, which is h by dk. So self.h, self.dk. As you remember, dk is basically d model by divided by h. So this multiplied by this gives you a d model. And then we transpose 1, 2. Why do we transpose? Because we prefer to have the h dimension instead of being the third dimension. We want it to be the second dimension, and this way each head will see all the sentence, so we'll see this dimension, so the sequence length by dk. Let me also write the comment here. So we are going from batch sequence length d model to batch sequence length h dk, and then by using the transposition we are going to batch h sequence length and dk. This is really important because we want each batch we want each head to watch this stuff, so the sequence length by dk, which means that each head we will see the full sentence, so each word in the sentence, but only a smaller part of the embedding. We do the same thing for the key and the value. Okay, now that we have these smaller matrices, so let me go back to the slide so I can show you where we are. So we did this multiplication, we obtained query key and values, we split into smaller matrices. Now we need to calculate the attention using this formula here. Before we can calculate the attention, let's create a function to calculate the attention. So if we create a new function that can be used also later, so self attention, let's define it as a static method. So static method means basically that you can call this function without having an instance of this class. You can just say multi-head attention block dot attention instead of having an instance of this class. We also give him the dropout layer. Okay, what we do is we get the decay. What is the decay? Is the last dimension of the query key and the value. And we will using this function here. Let me first call it so that you can understand how we will use it, and then we define it. So we want from this function, we want two things: the output, and we want the attention scores. So the output of the softmax. Attention scores, and we will call it like this. So we give it the query, the key, the value, the mask, and the dropout layer. Now let's go back here. So we have the decay. Now what we do is first we apply the first part of the formula, that is the query multiplied by the transpose of the key divided by the square root of decay. So these are our attention scores. Query matrix multiplication, so this @ sign means matrix multiplication in PyTorch. We transpose the last two dimensions. -2, -1 means transpose the last two dimensions. So this will become, the last dimension is sequence by sequence length by decay. It will become decay by sequence length. And then we divide this by math.decay. As we saw before applying the softmax, we need to apply the mask. So we want to hide some interaction between words. We apply the mask and then we apply the softmax. So the softmax will take care of the values that we replaced. How do we apply the mask? We just, all the values that we want to mask, we replace them with very, very small values so that the softmax will replace them with 0. So if a mask is defined, apply it. This means basically replace all the values for which this statement is true with this value. Okay, the mask we will define in such a way that where this value, this expression is true, we want it to be replaced by this. Later we will see also how we will build the mask. For now, just take it for granted that these are all the values that we don't want to have in the attention. So we don't want, for example, some word to watch future words, for example, when we will build the decoder, or we don't want the padding values to interact with other values because they are just filler words to reach the sequence length. We will replace them with -1 to the power of -10 to the power of 9, and which is a very big number in the negative range, and which basically represents -infinity. And then when we apply now the softmax, it will be replaced by 0. We applied to this dimension. Okay, let me write some comments. So in this case we have batch by h, so each head will, and then sequence length and sequence length. Alright, if we also have a dropout, so if dropout is not known, we also apply the dropout. And finally, as we saw in the original slide, we multiply the output of the softmax by the V matrix multiplication. So we return attention scores multiplied by value, and also the attention score itself. So why are we returning a tuple? Because we want this, of course we need it for the model, because we need to give it to the next layer, but this will be used for visualization. So the output of the self attention, so the multi-head attention in this case, is actually going to be here, and we will use it for visualizing. So for visualizing what is the score given by the model for that particular interaction. Let me also write some comments here. So here we are doing like this, batch and let's go back here. So now we have our multi-head attention, so the output of the multi-head attention. What we do is finally okay, let's go back to the slide first, where we are. We calculated these smaller matrices here. So we applied the softmax Q by KT divided by the square root of dV, and then we multiplied it also by V, we can see it here, which gives us this small matrix here, head 1, head 2, head 3, and head 4. Now we need to combine them together, concat, just like the formula says from the paper, and finally multiply it by WO. So let's do it. We transpose, because before we transform the matrix into sequence length we had the sequence length as the third dimension. We wanted back in the first place to combine them, because the resulting tensor, we want the sequence length to be in the second position. So let me write it first what we want to do. Batch, we started from this one, sequence length. First we do a transposition, and then what we want is this. So this transposition takes us here, and then we do a view, but we cannot do it. We need to use contiguous. This means basically that PyTorch to transform the shape of a tensor needs to put the memory to be contiguous, so he can just do it in place. -1 and the self.h multiplied by self.dk, which, as you remember, this is the model, because we defined dk to be here the model by h, divide by h. Okay, and finally we multiply this x by wo, which is our output matrix of x. This will give us, we go from batch to, and this is our multi-head attention block. We have, I think, all the ingredients now to combine them all together. We just miss one small layer. Let's go have a look at it first.